This video will serve as a very good tutorial and a guide for those who are interested in graph theory, Wolfram language, and in particular want to do some hobby project about Ramsey graphs and the Ramsey numbers. If you have any a graph theory book nearby, you open preface or in the first chapter, they always mention Ramsey number as a party problem. And the problem usually involve only 6 people. And the conclusion would be there must be at least 3 people know each other, or at least 3 people that will not know each other. And you probably will be surprised that all books mention this case, but they only stuck at 6 people in the party. The reason is this is an extremely difficult problem, and if you don't have a computer to help you to enumerate the numbers, you will probably only stuck at the really small cases. And even with the modern algorithm and a lot of research, I'm not aware of any efficient algorithm that explore this number to a much larger extent with a much larger graph. If there were, this web page probably will include something like 100 or Ramsey 100 or 400 or something like that. We won't stuck at 5 for only less than 10. But this is a still like remarkable survey of this topic using lots of effort from smart people in this research area of combinatorics. And you can tell it's really hard is, for example, in this case, you have something that is proven for 27 vertices, but enumeration is completed sort of 20 years later. So this is a very hard modern problem. I think this is a very good collection of resources that you can play with it and serve as a good exercise to help you understand how to use these existing resources with the Wolfram language. And by doing so, you can also understand a lot of jargons using in graph theory. So this should be serving as a very good tutorial for you guys. The first step is to download the data that you need for our hobby project. What I do first is set directory to notebook directory, so that once I download the file and save it with the same directory with this notebook, I can just call these files directly using the name instead of the full path. So that make it really easy to handle multiple files in this particular directory. So let's go back to the website. Say I want the file 366. So this is a 3, 6, and a 6. So this file should contain 37 graphs. So what I do is just right-click that and save the link as to the local machine. And once I have that, if you are on Windows machine, you can use this particular 7-zip function package. It's a free software, and you can click this folder and click the particular .gz compressed file that you need and click extract. So it will just extract the file into the directory and you can use that. If you're on Linux and Mac, you can use any type of untar or gzip command line tools to help you to decompress this file. And once you have the G6 file, you can directly import into Wolfram language using the import function. Usually, you don't have this option available for import. But if this is a graph format, G6 or other graph, the other one should be associated with discrete graph, a sparse graph type. And then in these two cases, you can use the option for graphs directly inside the GL function. So you can see the GL contains 37 elements using the length, and the GL example is I can using the random choice function to sample 5 from the list. If you want to check everything, you can simply remove the length here, and it will print out all the files, all the graphs for you. Okay, so you have all the available graphs, Ramsey 3.6. So what does this mean? So let's go back to the definition. It says the Ramsey 366, so S equal to 3, T equal to 6, and with 6 vertices, is a graph with 6 vertices. There are no cliques of size 3. So in this case, there is no triangle and no independent sets of size T. What this means is you have 6 people in the graph and none of them know each other. So this is the A, not A, and not B, which is the complement of the condition in the original Ramsey number, which says at least M will know each other or at least N will not know each other. So this is A or B. So here is not A and not B. So logically, the Ramsey STN graph is a graph that avoids the Ramsey number. Okay, let's continue our data importing process. So if you want to change the graph that you imported to some other style, you can also do that after it's imported. So you simply wrap, for example, the last element of the list, this guy, like fish, into a graph function and specify vertex style to red. So you can update the color of each nodes from this standard blue to the red. So far, I've shown you the first way of importing. There is another way to do that. And it's quite essential if you want to do this type of visualization or graph analysis efficiently inside Wolfram Language. So for the first one, I can do directly is because the number of lines in that file is really small. And in Wolfram Language, if it's imported directly, it basically converts all the lines into graph like this. So if I have hundreds of thousands of graphs, so it immediately will eat my RAM or the system heap immediately, because these objects are dynamic. If it's like SVG graph, so it contains a lot of information to make the vector. So it's really not efficient to store them directly. So I want to just keep the strings and convert them into the graphs that I need on the fly. So the way you do that is using the open read function. It's like C++ string function. It's kind of low level, but it gives a way to efficiently import a large amount of string data into the system. So you open the stream, stream. I store it here, and using read list to extract the items line by line, and then close the stream. So in this case, everything in stored data will look like this. It looks like alien language, really does not make sense. But if you import each string back into Wolfram Language using import a string function and give the specified second argument, graph 6, optional item in the third place, you can convert those strings back into the graphs like this. This step is valid because the original file, the r3613.g6 itself looks like a list of alien language, but everything is simply a string. To view this data directly inside Wolfram, you can just use the data variable and apply a short here so that I do not have overwhelmingly large number of elements displaced here. The other way to do that efficiently is to use a new tabular function after version 14. And this comparing to the raw data storage using list of string, it saves your space quite a lot. So this is sort of a recommended way if you want to handle large number of data with the same type. And you can also verify that with the tabular schema function. It's like a schema function in all SQL database. It gives you a summary of the column and the element type in that column. So I have pre-released the data, so the variable does not look like this color, so it indicates it's undefined. And we can also quickly check the number of items in the tabular. Simply wrap length as outside of tab, the variable. 275086, it's 275086 here. So it matches correctly. So one application of this is I can use this tabular as a random function generator, and the random function generates a random graph. And the graph here guarantees that it's R366 with the 6 vertices. So this is sometimes very useful if you want to generate random stuff with a very strict specification. So what I do is using tabular element and give it random integer. So this integer, I hard coded with this value. So you can, this function, length function of tabular, directly here to make more adaptive if you want to change the size of the tabular. And once it generates an outcome, it gives you something like a data set. So use normal function to convert into an association and extract the value associated with the G13 key, which is just the name of the column. So by this way, you can generate a random function that for you to create this type of random graph. And using the same procedures we have before, convert this random string into a graph. So you can run that multiple times. It will give you some of the random graph specifically associated with R366. You can do the same thing for all the vertices. So the next step is, once I have those graphs imported in the system, I want to check if they indeed satisfy these R36 properties. And of course, you can do the same thing for all other graphs. Okay, for example, really into this particular graph. So I just copy it and paste it into input cell and assign it to G1 as a name of variable. So the first step I want to check is whether it is free of 3 clique. 3 clique is 3 complete graph. So if you only have three vertices and you have a complete graph, it simply means it's a triangle. So R36 means I should have no triangle. Or the other way to say that is if I pick all the clique inside this graph up to 13 vertices, because only I have 13 vertices here. And all the clique I have should have at most 2 points. So indeed, all the clique you have here composed of 2 elements, which is just simply a line or the edge of the original graph. I don't have 3 vertices list. So which means it is indeed 3 clique free or triangle free in our case. You do the same thing for this guy. Find independent vertex set. So you can also go back to your web page, or you can just hover your mouse over the function name and click the book sign here. It will bring you to the documentation of this page. So this syntax means find independent vertices. That's the people who does not know each other. And the 13 is the maximum of number of vertices. The vertices are like at most of 13, sort of a brute force. I check all the possible sets. All means everything. What I expect is if you check the definition here, the 6 means there's no 6 people who does not know each other, which means there's no line connecting to them. And the maximum length of such vertex set is at most 5. So you see the 3, 4, 5, 9, 3, 13. Let's take a 3, 4, 5, 9, and 13. Well, this is a kind of illusion because you have 5, 6, and 6, 4, but there's no direct link between 4 and 5. So this is a set with people who does not know each other, and the maximum value, the maximum length is simply 5. So if you do that by yourself, one by one, it's tedious. So let's use function length and map to all the elements above. So you can see the maximum is 5. We can do the same exercise again for a new graph. So I use tabular and then generate random number and pick one random number as index to select this random graph using the import string and graph6, and assign it to vertex name and image size inside the graph function outside of it. So we can quickly check if it's indeed R366 or 3613. So in total we have 13 elements for vertices, and the largest clique. So by default, if we do not add anything to the second argument or third argument inside functions, they always looking for the largest available clique or independent set. So in this case, we have 1, 7. It's simply an edge, so it's triangle free. And for the largest independent vertex set, it's 1, 2, 3, 4, 5. Let's see. So 1, 2, 3, 4, 5. There are no line connected to them. So this is indeed independent set. So be aware of that. For the items in the list, it simply means there is no direct connection. It does not mean there is no path. For example, 2, 3, or you can argue that 2, 3 is actually sort of linked, because I can go to 3 from 2 in 2, 6, 3. Okay, this does not count. So you must have direct connection for it to be excluded in this set. The project we can do in this video is about maximal graph. So maximal is quite different from maximum graph. The maximum is usually much more difficult than maximal. The reason you can see here, it's long time proved that 27 is maximal, and also the maximum, the largest Ramsey number for 3, 8 can have at most 27 vertices. So this is the maximum. And for maximal here, we can check actually quite easily using the current system, is by simply say if we add an edge or add a vertex into any given like vertex graphs listed in this case, then we will have something break for the condition here. So, but in particular, if we have adding an edge then we must have a triangle inside this graph. So in R38, it's triangle free. If we add just one edge internally, it must contain a triangle. If we add external vertex, for example, then it is not R3 either. We either have a independent set with at least 8 elements, or if we add edge between the old graph and the new vertex, we will have a triangle. So in this way, we can show that 27 is maximal. All right, it's not able to show that it is maximum using this method. And the other question we have is, what about drop? Because in the original Ramsey graph, people know each other is a red line, and people don't know each other is green line. And adding green line means drop of a red line, okay? So in this case, we can actually drop it and still have it as R38. The reason I think is from the name, it says it's the maximal R38. But if we think about dropping edge, it's actually complement graph of R38. So that one is actually not maximal. Okay, let's try our test in action. Okay. So I just copied this graph into a new notebook. Okay. The first, let's test if it's possible to add edge. So first, we can check it's indeed a graph with 27 vertices. So use the vertical list of G3. The G3 is the graph here, and it's 27 items. Okay, and then let's check the number of edges here. So you can see it's a list of all the undirected edges. We can also quickly count the number of edge here. It's EL, it's 90 edges. Okay. So we want add one more edge inside this graph. How we do that? Recall that the maximum edge you can have in a simple graph is CN2. It's a binomial N2. You choose 2 elements from n vertices. Okay, so I is from 1 to 26 and j is from I plus 1 to 27. So this is to give you all the possible edges you have. And this is basically enumeration of all the binomial numbers. And the missing edge is simply all possible edges complement with the edges that I have. So we can take a look at it. This is all the edges that's possible to link any 2 vertices minus the edges that are already linked. So this gives you the whole list of complements. So we can run that again with the compound expression to eliminate the output. So you can just randomly choose a missing edge, ME1, just to give you a name, and we add it back into the edge list. And so we can see that it immediately gives you A859 as a clique or triangle. So this actually gives you every different value if you run that, because I just use random choice. So if you want to repeat the result, you can add seed random to it, so that every time you have predictable result. And you can just visualize the graph on the original graph. For example, I can just run this code. For example, I need to put 859 inside this area. You can immediately see that I have a triangle here. The triangle here, right? And the vertices are labeled with diamond, and the edges are highlighted in red. So you can see clearly there's a triangle. So this is no longer a triangle-free graph. Okay. And for external vertex, it's actually really simple. We can show that it is really not possible. Let's go back to our graph. Why it is not possible is, say, let's do find independent vertex set for G3. And because we know it's R3, 8, I can just cheat, put 7 here. And this is all the list of the independent sets. Okay. Now let's show that it is not possible to add one more vertex outside. The reason is actually quite simple. If I just add a graph or a point on the outside and connect nothing, then it must be inside these independent sets because it connects to nothing. So it's safely we can add it into this list. So apparently we will have a list that's more than 8 items, or at least 8 items. So this definitely breaks this guy, okay? The other issue is how to just avoid that point to be added to these lists. Well, it is very simple. Assume the new vertex is 28, and it must connect to at least one of the elements in each list. The reason is if 28 only connects to, say, 23 and 24, but nothing in the second list, then 28 can be added into the second list because it's part of the independent set. So it connects to none of the elements inside. So it must connect at least one above and one lower. So now here is the key step. Is for two elements, that's two sets that are different, there must be an element that's not the same in both lists. So for example, 24 and 27 in this case. All right. So the key here is you realize that once this 28 connect to 24 and 27, then we must have a triangle because 24 and 27 are not independent. If they are independent, they must be in the same set. But if not, they must be in separate set. So in this case, 24, 27, and 28 form a triangle. So what about just connect 28 to 10? Well, this is not possible. Why? If 10 is an element in all lists, what I mean is all lists here. What does it mean? It means 10 must be an isolated point. But because our graph is connected, so this is not possible. So in this case, we conclude that it is not possible to add another vertex so that to keep it R3, 8. Or in other words, you add one point, and if there's no edge attached to it, then it breaks the 8 part. So you have longer independent set list. And you attach an edge in that inside, we must have triangle. And this is not possible because 10, there is no such element shares the independence set with all other elements. So this concludes our proof that indeed the graph we have here is maximal. So this proof is a strong demonstration about the mixture of computational evidence and some of the logics. And for the rest part, if we want to do the same thing for the dropping part, we can actually drop one of the edge so that R38 is still valid. This can be shown in the computational evidence in my following example. So it's almost the same code as above, but instead of adding edge, I just use a delete function to remove one edge from the graph. And then you have a list of independent vertices. And this list is still of the length 7, which is also the maximum. So this says if we drop one edge, the number of the maximum independent center probably not going to increase in our case. You can count the number of vertices, the star vertices in the graph, and you see no red line between them, which means there's no edge. So we still have a maximum independent set of length 7. So in this case, we show that the complement graph is not actually maximal. And you can use the same computational tool for all other examples in the original web page. Hopefully you enjoyed the lecture. See you next time.